The median U.S. software developer specialist salary is $110,140 US dollars annually, and per hour pay is almost $53 US dollars. Software engineering jobs are also a great way to start on your path to a high-paying career in information technology. This course has US 3 software developer specialist salary is $110,140 US dollars annually, director and at IBM pay is the architect for several IBM professional certificates. Bethany is an instructional designer at Skillup Technologies, and Lynn is also an instructional designer at Skillup Technologies. So, what's in this course? It's divided into 5 modules: the software development lifecycle, Introduction to Software Development, Basics of Programming, Software Architecture, Design and Patterns, and Job Opportunities and Skill Sets in Software Engineering. When you complete this course, you'll be able to describe software engineering and approaches to software development, identify software development tools and technologies, compare different types of programming languages and recognize basic programming constructs, outline approaches to application and deployment architectures, and review the skills required in software engineering and describe the career options it provides. During this course, you will learn through guided instructional videos that walk you through key concepts with essential need-to-know facts, interactive exercises to reinforce what you've learned in videos, insider viewpoints that enrich your understanding of IT support work, practice assessments to help you gauge your knowledge, and finally, graded assessments to prove what you've learned. Upon successful completion of this course, you'll earn a shareable badge and certificate that you can show to prospective employers. We're here to support your success. If you have any questions for the course staff, or if you want to connect with your peers in this course, please feel free to post on the course discussion forums. We're excited you're here. So let's get started. Welcome to Meet the Experts. In this course, you will learn from several experts in various roles who will provide their insights and perspectives about software engineering. Let's meet these experts and learn about where they work and what they do.
Hi, my name is Kadesha, and I currently work as a developer advocate at GitHub.
Hey, well, my name is Liseli Bueno. I'm a software engineer, and I work at Blend, also known as Blend Labs.
My name is Tommy Young. I'm a software engineer at Google. My role is Uber technical lead, overseeing publisher video ads.
My name is Diane Panagiotopoulos. I am a research and development engineer at Bandwidth, and I work directly through Bandwidth. I am not self-employed as like a contractor with them.
Hi, my name is Zubin Pratap. I'm a software engineer and currently I'm a developer advocate at a Web3 startup.
My name is Daniel Rudnitsky, and I'm a full-stack software engineer at IBM.
My name is James Reeve, and I'm a full-stack software engineer at IBM.
Hi, my name is Rupinder, and I work as a Chief Solutions Architect at Skillup Technologies.
Hello everyone, my name is Upkar Litter, and I'm a developer advocate with IBM.
Hi, I'm Jan Stoneman. I'm a solution architect at Smartronix.
Now let's listen to some of these experts describe a little more in detail about what they do.
Yes, so a developer advocate is a software engineer who enables developer to be successful with a product. That was a mouthful, so essentially what that means is, for example, at GitHub, I create a lot of content. So I will do blog posts, workshops, go to conferences to speak about GitHub, the product. I'll also showcase developers in the open source community and to like give publicity to the projects that they're working on. And being an advocate means that I'm able to communicate deeply about technical concepts in a way that's digestible for engineers across experience level to understand. Before I was an advocate, I worked as a software engineer in the finance sector for 2 years. I spent a majority of my time coding. I primarily worked on the front end of the application using tools such as Git, Docker, GraphQL, React, JavaScript, and the very few times I would go into the backend, we use Node.js on our backend to make changes and updates. My experience as a software engineer and also as a technical content creator paved the way for me to become a developer advocate at GitHub today.
I'm a software engineer right now. I'm still pretty junior, so most of my tasks involve creating new features, fixing bugs, and addressing any customer concerns that they have with the current software.
lekin ovoz bilan va chatdagi ikkalasi vasiyat. Menimcha bu shu mavzu. AirPods ham bilan.
I didn't get that. Could you try again?
Mikrofon olish kerak ekan demak. Alaykum assalom. Yaxshimisiz? Charchaysizmi? Ovozingizni qilamiz. Taxminan 20 sekund, 30 sekund gaplarim kech yetib boryapti lekin. Chatda yozsamchi. Tiniqlashdi lekin past. Shu menimcha shu mikrofon olishim kerak ekan. Bo'ldi, shuni test ko'ray deganimda rahmat, charchamanglar.
Yeah, so I work on a suite of products that are they're targeted to large content creators, video publishers. Customers such as ESPN, Disney, etc. And we basically have suites of tools to help them monetize their video content, help them distribute it, help them target it appropriately, report on it, troubleshoot it for across all devices, all surfaces. So it's kind of a full suite of products. It starts with the user interfaces that their sales teams and trafficking teams use to sell the ad space, upload the creatives, the advertisements, and target them to their audiences and contextually to the content that they're that they create. We offer reporting on that, so a lot of it's performance and various other analytics, reach analytics, and so forth.
Previously, before this, I was a software engineer at Google, and before that, I was a software engineer at a small startup. But before that, for about over 15 years, I was a corporate lawyer and then a business executive for a while, and I even had my own startup in the middle. So yeah, very diverse background. And I taught myself to code in my very late 30s when my startup started to fail, and I really needed to keep it going, and my tech co-founder quit. So that's what I do. That's who I am. Today, as a developer advocate, I not only write code, I also produce a lot of educational content and material that is useful for people to onboard onto Web3 and other technologies. And my role is really to help connect the product team with the actual developer ecosystem, bring the two together through code, content, education, and community.
Welcome to What is Software Engineering? After watching this video, you will be able to define software engineering, list the responsibilities of a software engineer, and compare and contrast software developers and software engineers. Software engineering is the application of scientific principles to the design and creation of software. The field uses a systematic approach to collect and analyze business requirements in order to design, build, and test software applications to satisfy those business requirements. When computing began in the late 1950s, software engineering was a relatively undefined discipline, but over time it transformed into a modernized engineering field. The software engineering field became a discipline in the 1960s and evolved as new technologies were developed and the approach to software development became more scientific. Trends in software engineering transformed from ad hoc programming towards more formal and standardized methods. Initially, the creation of software lacked a formal development process. As the world widely adopted computers, software became increasingly integral to more aspects of life. The inefficiencies in the software development process made it difficult to meet the rapidly increasing demand for computing resources and complex software. This led to what is known as the software crisis, which began in the mid-1960s and lasted until the mid-1980s. During this period, software development often ran over budget, behind schedule, and consisted of unmanageable, buggy code. By the time older software solutions came to fruition, newer, better, and faster technologies had already been developed, causing software engineers to have to refactor their code or completely redesign their system. Often software development solutions that worked for small software systems did not scale to large complex projects. Now, some of these issues still exist today, although to a much lesser extent, due to the consistent application of engineering principles to the software development process. Computing resources have become more widely available, and standardized methodologies for software development allow for large complex solutions that scale. The solution to the software crisis involved transforming unorganized coding efforts into an established engineering discipline. The mid-1980s also saw a rise in the growth of computer-aided software engineering, or CASE, which also helped to relieve the software crisis. CASE tools can be divided into 6 categories: business analysis and modeling, development tools such as debugging environments, verification and validation tools, configuration management, metrics and measurement, and project management. Now, the term software engineer is often used interchangeably with software developer, but there are subtle differences. Software engineers are also developers, but the term software developer is usually deemed narrower in scope than that of a software engineer. A software engineer's knowledge is usually broader. Software engineers take a systematic big-picture approach in their thinking to software development, whereas developers may have more creative approaches. And both software engineers and software developers have specialized knowledge, but software engineers use that knowledge to build entire systems, whereas software developers use their knowledge to write code to implement specific functionality within a system. Software engineers are often employed on larger scale projects, and they are focused on the broad structure rather than solving an immediate problem. Software engineers are tasked with designing, building, and maintaining software systems. Their responsibilities include writing and testing code and consulting with stakeholders such as clients, third-party software vendors, security specialists, and other team members. The adoption of a measured scientific approach to software development has influenced the way software is created and designed. Today, the development process is typically guided by the Software Development Lifecycle, or SDLC. The SDLC identifies the steps needed to develop high-quality software. Later in this module, we will discuss the SDLC, the traits of high-quality software, and roles common in the field of software engineering. In this video, you learned that software engineering is the systematic approach to design and development of software. Responsibilities of a software engineer include designing, building, and maintaining software systems, writing and testing code, and consulting with stakeholders, third-party vendors, security specialists, and other team members. And finally, software engineers build systems while software developers implement specific functionalities. Welcome to Insider's Viewpoints. What is software engineering? In this video, we will hear from experts discussing software engineering.
I think software engineering is the process of using programming languages and engineering principles to build products. These products could look like web apps, mobile apps, desktop apps, operating systems, or even networking systems. It is a skill that's integral to the success of our modern society because without technology, we couldn't get a lot of things done today. Within software engineering, it's a very broad term. And so within software engineering, you have roles such as front-end, back-end, security, mobile, test, full stack, DevOps, cloud, data, and machine learning. And these are all different types of engineers within software engineering.
I would define software engineering as building and improving software from anywhere from design and architecture to the user interface to fixing small bugs. So anything that falls in that range, that's what software engineers do.
So software engineering to me, I think really has to do with, I consider it a creative process, and it fundamentally is the practice of designing, envisioning, implementing, and then supporting and maintaining software through the full life cycle of it. So not just writing code, but in thinking about the software you're building before you've even written a line of code, the journey from idea inception to actual implementation and launching of said software, and then maintaining it, improving it, supporting it, and potentially evolving it to something else. So it's very much a sort of creative and full life cycle end-to-end engineering process.
I know in the United States, at least, software engineering, software development, programming, they all have, depending on who you ask, they mean very specific things or very hazy things or very contradictory things, or it's like, why do we even have 3 different titles for the same thing? I think of those titles as kind of all meaning the same thing.
What's the difference between a software engineer and a developer?
I think the difference for me, I consider engineering to be a little bit sort of broader, software engineering to be broader than development. I think development to me means is sort of one part of the process. So I think one fundamental difference for me is I think software engineering is beyond just writing code, which I think a developer often is handed a task to write a piece of code, create a module, piece of software, whatever term you want to use. And I think engineering involves sort of starting, a very long time before you would even get to the development process, and continues on beyond the time you would actually take your code, deploy it. So this kind of goes into the full life cycle.
In my opinion, there isn't a difference really. So for example, I was trained as a full stack engineer or a full stack developer, but I was hired as a software engineer to work on the front end of the company's application. So I think it's a matter of semantics, and a lot of it I think is a lot of gatekeeping to keep people who don't know anything about the industry out. Somebody who has studied CS may argue differently from I do, but as a person with a non-traditional path into the world of software engineering, I only see it as like title changes and title differences, and I think it depends on what company you work in and what company you work for, because at the end of the day, we're all using the same tools and technology to get the product shipped to production.
I think that they are pretty similar roles. They are used interchangeably a lot, I think. But I think the main difference is that software engineers are also responsible for the system design and architecture, as well as data, how it's received, used, and how it's disseminated, whereas software developers, I think, focus more on the building of apps and features.
So in Canada, being a computer programmer or a software developer is incredibly different than being a computer engineer or a software engineer, where to be an engineer, it means you've taken specific classes in like codes of ethics, and you're held to the same ethical standards as a civil engineer or a mechanical engineer. And so depending on where you are, the titles can mean very different things. And I know for like purposes of immigration, the titles also can mean very specific things, and you have to be careful about like what it is that you put down. But in job descriptions, I kind of see them all used interchangeably, and I tend to just kind of think of them all as the same thing.
It's much more of a longer time horizon, I think, in terms of engineering versus development. And I think there's a lot more considerations and hats you need to put on throughout the software engineering life cycle versus the kind of more narrowly scoped development cycle.
Welcome to the Introduction to the Software Development Lifecycle. After watching this video, you will be able to describe what the software development lifecycle is, explain its history, and discuss some key advantages of using it. The software development lifecycle, known as the SDLC, is a systematic process to develop high-quality software in a predictable timeframe and budget. The goal of the SDLC is to produce software that meets a client's business requirements. The SDLC defines phases of the software development process that encompass their own process and deliverables. It's a cycle of planning, design, and development that can be implemented as an iterative approach to software development. Adherence to the SDLC minimizes risks and costs to the development of high-quality deployable software. The software development lifecycle began to take shape in the mid-1960s as software development began to necessitate a more detailed approach because of its growing complexity. The SDLC led to a more deliberate approach as large corporations needed to manage complex business systems requiring heavy computational resources. In its initial conception, it used what is called the waterfall method to manage projects where the development of software follows a linear pattern through discrete stages. The SDLC has since been adapted, however, to more iterative methods in response to addressing customer needs and shifting requirements. Waterfall and other approaches to software development will be discussed in another lesson. There are some key advantages for businesses in following the SDLC. The first advantage is that it gives development teams a process to follow rather than using an ad hoc approach to improve efficiency and reduce risks. Secondly, there are discrete phases to the SDLC. Each phase is well defined so that team members know what they should be working on and when. The phases of the SDLC will be discussed in another video. Because of the well-defined phases, it facilitates communication between the customer, other stakeholders, and the development team. The SDLC offers an overview of the process so stakeholders know where they fit into that process. Also, since each phase is discrete, cross-domain teams know when they have completed their tasks and when development can move to the next phase. The SDLC provides room for iteration, where, at the end of a cycle, the process can circle back to incorporate additional requirements as needed. Problem solving is incorporated early in the cycle, so problems are addressed in a timely fashion and can be addressed in the design phase rather than during coding. Finally, each team member has a well-defined role which reduces conflict and overlapping responsibilities. In this video, you learned that the SDLC provides a systematic process for software development. Its initial development in the 60s and 70s was driven by the need for a systematic approach because of the growing complexity of software. And key advantages of the SDLC include a roadmap to the software development process helping to reduce risk and improve efficiency, increased communication between the team and stakeholders, clearly defined and understood responsibilities for each team member, and the ability to be used iteratively, allowing for changing requirements. Welcome to the phases of the software development lifecycle. After watching this video, you will be able to name the phases involved in the SDLC, describe each phase, and identify several tasks associated. With each phase. There are generally 6 phases in the SDLC process: planning, design, development, testing, deployment, and maintenance. Each phase is discrete, meaning that tasks from a previous phase do not overlap with tasks in the next phase. The original SDLC was conceived as a traditional waterfall method, where the phases are linear, but have since been adapted to introduce iteration so that shifting requirements can be accommodated. Waterfall and other approaches to software development will be discussed in another video. Note that some organizations may have different names for each stage. For example, planning may be called requirements or strategy or analysis. Also, some organizations may have additional or fewer stages. In the first stage of the SDLC, the planning phase, requirements are gathered, analyzed, documented, and prioritized. When planning a software solution, the following factors must be considered: users of the solution, the overall purpose of the solution, data inputs and outputs, legal and regulatory compliance, risk identification, quality assurance requirements, allocation of human and financial. Financial resources, and project scheduling. As part of the planning process, labor and material costs are estimated and weighed against time constraints. Also, project teams are identified and roles of each team member are proposed. If stakeholders are struggling to define requirements, often the development team may produce prototypes during the planning stage to tease out those requirements. A prototype is a small-scale replica of the end product used to get stakeholder feedback and establish requirements. A prototype is used to test basic design ideas. Though prototyping usually occurs during the planning stage, prototyping can occur at various phases of the SDLC whenever requirements need to be reconsidered or clarified as the project develops. After requirements have been gathered, they are combined into a document called a Software Requirements Specification, or SRS document. The SRS needs to be clearly understood and approved by all stakeholders. The developers are also involved at this stage so they can gain a clear understanding of these requirements. Requirements and the SRS will be discussed in more detail in a later video. In the design phase, the requirements gathered from the SRS are used to develop the software architecture. Several team members work together at this stage to design the architecture. The architecture is reviewed by the stakeholders and team, and during this phase, prototypes can be designed. A prototype is a preliminary mock-up of the system or parts of the system used for demonstration purposes. The document created in this phase is called a design document and is used by developers during the next phase, which is the development phase. The development phase, sometimes called the building phase or the implementation phase, is when the developers start the coding process once the design document is completed. The project planners use the design document to determine and assign coding tasks. This phase often requires the use of programming tools, different programming languages, and software stacks. Organizations may also have standards or guidelines that need to be followed. The testing phase is next in the process once the coding is complete. and some large projects have dedicated testing teams. Code needs to be thoroughly tested to ensure it is stable, secure, and meets the requirements outlined in the SRS. Testing can be manual, automated, or a hybrid of both. Product bugs are reported, tracked, and fixed, and the code is retested until the software is stable. Some common levels of testing include unit testing, integration testing, system testing, and acceptance testing. Each of these testing levels will be described in further detail in another video. Next, the deployment phase is where the application is released into the production environment and made available to users. This can also happen in stages. First, it is released onto a user acceptance testing, also called UAT, platform, and once the customer signs off on the functionality, it is released to production. This approach can be used for making software available on a website, mobile device app store, or a software distribution server on a corporate network. Finally, the maintenance phase happens once the code has been deployed into a production environment. This phase helps to find any other bugs, identify user interface issues, or UI for short, and identify other requirements that may not have been listed in the SRS. Code enhancements can also be identified at this stage. If bugs are discovered in this phase that were missed during testing, these errors may need to be fixed for high-priority issues or incorporated into the requirements as part of a future software release, and the process can start over again. In this video, you learned that the SDLC can be divided into 6 phases. Planning involves requirement gathering and development of the SRS. The architecture is developed during the design phase, and the design document is created. The development phase is when coding takes place, and then during the testing phase, issues with the code are found and fixed if possible. Deployment is when the code is released to the production environment, and finally, in the maintenance stage, feedback is collected from stakeholders, other UI issues may be identified, and code enhancements suggested. And this information can be fed into another software development cycle if necessary. Welcome to Building Quality Software. After watching this video, you will be able to list common software engineering processes and describe the common software engineering processes required for building high-quality software. There are numerous processes that are common to software engineering projects. In this video, we will discuss 6 of them: requirements gathering, design, coding for quality, testing, releases, and documenting. The Software Requirements Specification, or SRS, encompasses the process of collecting and documenting the set of requirements that the software needs to adhere to. It may include a set of use cases that describe the business needs and user flows that the software must implement. Software requirements can be classified into 4 broad categories: functional, external and user interface, or UI, system features, and non-functional. These categories are discussed in more detail in another video. Software design is the process of transforming the requirements into a structure that is implementable using code. The software design process translates the requirements into a language the developers can use to write the code. It transforms the requirements into a software solution. The technical lead breaks down requirements into sets of related components with clearly defined behaviors, boundaries, and interactions. These components define the system architecture. The system design incorporates guidance on system functions, performance, security, and platform characteristics. The design communicates business rules and application logic. Application Programming Interface Design, which is how apps talk to each other or communicate with the database, user interfaces, and database design. Code quality refers to the characteristics of the code, including attributes such as maintainability, readability, testability, and security. Quality code must fulfill the intended requirements of the software without defects. Additionally, it should be clean and consistent, easy to read and maintain, well documented, and efficient. Coding for quality entails following a set of coding practices during development. These include following common coding standards, conventions, patterns, and styles, using automated tools known as linters to detect pragmatic and stylistic errors, and commenting in the code itself to make it easy for others to understand and modify. Software testing is the process of verifying that the software matches established requirements and is free of bugs. Its purpose is to identify errors, gaps, or missing requirements when compared with stated requirements. Properly tested software ensures reliability, security, performance, and efficiency. Software testing can often be automated or done manually. Levels of testing include unit, integration, system, and user acceptance. Unit testing is often done by the developer and tests the smallest component of code that can be isolated from the rest of the system. Once components are integrated into the larger product, integration testing occurs. Then, after the larger product is deemed completed, system testing can take place. User acceptance testing, or UAT for short, and sometimes called beta testing, is when the software is tested by the intended end user. Types of testing can broadly be divided into 3 categories: functional, non-functional, and regression. Testing levels and types will be further explained in an upcoming video. When the newest version of the software is distributed, it is referred to as a release. Different types of releases are intended for different audiences. There is generally an alpha, a beta, and a GA release. GA stands for General Availability. The alpha release is the first functioning version of the system released to a select group of stakeholders. The alpha release likely contains errors and may not contain the full feature set, but does contain most of the desired functionality. Design changes may still occur during this release stage. The beta release, also called a limited release, is given to the stakeholders outside of the developing organization. One of the intents of the beta release is to try out the software under real conditions, test the functionality, and identify any outstanding bugs or errors. The beta release should meet all the functional requirements. Then, after beta release, changes are agreed upon, made, and tested, and a stable version is released. The audience for the GA release is all users. Software documentation should be provided to both non-technical end users and technical users. System documentation is geared toward the technical user. Technical users may be other engineers, developers, or architects. System documentation explains how the software operates or how to use it. It consists of README files, inline comments, architecture and design documents, verification information, and maintenance guides. User documentation is provided to the non-technical end users to assist them in the use of the product. Generally, user documentation is provided in the form of user guides, instructional videos and manuals, online help, and inline help. More details about documentation will be discussed in another video. In this video, you learned that requirement gathering is collecting and documenting the set of requirements that the software needs to adhere to. Designing transforms requirements into a structure that developers can use. Coding for quality entails following a set of coding practices during development. Testing is the process of verifying that the software matches established requirements and is free of bugs. There are 3 types of releases, including alpha, beta, and general availability. And finally, documenting requires text or video that explains the software to technical and non-technical users. Welcome to Requirements. After watching this video, you will be able to describe the steps of the requirement gathering process, explain the purpose of a user requirement specification or URS document, explain the purpose of a software requirement specification or SRS document, and explain the purpose of a system requirement specification or SysRS document. Requirement gathering is a 6-step process of defining a problem to be solved and documenting how to go about solving that problem. These steps include identifying stakeholders, establishing goals and objectives, eliciting requirements from the stakeholders, documenting the requirements, analyzing and confirming the requirements, and prioritizing. Generally, the stakeholders work for the organization that requests the development of the software product. Key personnel from the organization may include decision makers, end users, system administrators, engineering, marketing, sales, and customer support personnel. It is good to have a representative from every group that the product affects. The goals of the product should be clearly defined. Goals are broad, long-term achievable outcomes. Goals can include customer outcomes and business goals. Next, objectives should be identified. Objectives are more specific than goals, and they are actionable and measurable actions that achieve the stated goals. The next 3 steps, eliciting, documenting, and requirement confirmation, are usually completed iteratively. Elicitation can be accomplished through surveys, questionnaires, and interviews. As the requirements emerge, they should be documented and checked to ensure they align with the goals and objectives. Documented requirements should be easily understood by stakeholders and the project team. In order to confirm the requirements, they should be analyzed to ensure consistency, clarity, and completeness. And after analysis, the requirements should be shared with and approved by the stakeholders. After confirmation, requirements should be prioritized. Labels such as must-have, highly desired, and nice-to-have are helpful. If possible, order the requirements within those categories. Typically, there may be 3 documents that result from the requirements gathering process: Software Requirement Specification or SRS, User Requirement Specification or URS, and System Requirement Specification or SysRS. The most common of these is the Software Requirement Specification. The Software Requirement Specification, or SRS, is a document that captures the functionalities that the software should perform and also establishes benchmarks or service levels for its performance. Parts of an SRS include a purpose statement that contains the intended use of the SRS, its audience and scope, constraints, assumptions, and dependencies, and requirements which can be sorted into 4 categories: functional requirements, external interface requirements, system features, and non-functional requirements. The product's purpose describes who will have access to the SRS and how they should use it. The scope describes the benefits of the software, its goals, and objectives. And the second part of the SRS should detail constraints, assumptions, and dependencies. Constraints describe how the product must operate under given conditions that may limit options in the design phase, such as conformation to standards or hardware limitations. Assumptions may include things like a required operating system or hardware that is needed by the software to function. Dependencies on other software products should also be noted. Requirements can be classified into 4 categories. Functional requirements are those that cover the functionalities of the software. External requirements are the requirements that address the behavior of the software in relation to external entities, such as users and interactions with other hardware or software. System features are a subset of functional requirements. These are required features for the system to function. There are also non-functional requirements, such as specifying performance, safety, security, and quality standards. User requirements describe the business need and expectations of the end users from the software system. The user requirements are written as user stories or use cases that answer 3 questions. Who is the user? What is the function that needs to be performed? And why does the user want this functionality? User acceptance testing determines if these requirements have been met. Often, though, the user requirements and software requirements are combined into a single SRS document. The SRS details the expectations of the software system. The System Requirement Specification Document, or SysRS, to differentiate it from the SRS, clearly outlines the requirements of an entire system. The System Requirement Specification is often used interchangeably with Software Requirement Specification, but the SysRS is actually broader in scope than the SRS. Many software projects develop an SRS rather than a SysRS. The SysRS contains system capabilities, interfaces, and user characteristics. It also may include policy requirements, regulation requirements, personnel requirements, performance requirements, security requirements, and system acceptance criteria. It also outlines expectations of the hardware needed for the system in addition to software requirements. In this video, you learned that the requirement gathering process entails identifying stakeholders, establishing goals and objectives, and eliciting, documenting, confirming, and then prioritizing requirements. The SRS documents functional, external, system, and non-functional requirements. The URS documents user stories. And finally, the SysRS documents system capabilities and acceptance criteria, and policy, regulation, personnel, performance, security, and hardware requirements.
Everything is waiting.
Qanaqa mashina olishni xohlagan bo'lardingiz?
Qanaqa mashinaga erishtirgan? Software development methodologies, software version, software testing, software documentation, roles in the software engineering projects, insiders, job roles in software engineering teams, the software building process and associated roles. Qandoq kunga qoldik? Odamlarda na shafqat bor. Gapirganlarimiz videoga yozilyapti. YouTube'da stream boshlab qo'yganimda. Nima qanaqa? Odamlarda na shafqat bor. Gapirganlarimiz videoga yozilyapti. YouTube'da stream boshlab qo'yganimda.
Welcome to Software Development Methodologies. After watching this video, you will be able to list several commonly used approaches to the software development lifecycle, explain waterfall, V-shape model, and agile methods, and compare the pros and cons.
Aylangan chiqib ketamiz ko'chaga. Aylanib ketamiz. Bo'libdi soat. Qayerga chiqib ketsak bo'ladi? Piyoda. Hozir mana bunaqasini qilib, bunday aylanib keling. Yurib ketdim mana. Ko'chaga chiqsak, tashlashdan tabiatga osiladi, chunki florasi. Yotmadim bu. Karbikan noldan olib kiramiz. Karbikan noldan olib kiramiz. 11 gacha bo'ladi, yozga ochiq bo'ladi. Orqamizdaga o'tsak, yarim soatga yetib boramiz. Bo'ladi. Ertaga davom etamiz. Xullas, bugunga tamom. Sog' bo'lasizlar, salomat bo'lasizlar. Bugungi stream tugadi. Ha?